Hi, today we're going to talk about the periodic table and what kind of elements are found inside it. First, before we get too far into things, a bit of a reminder, a refresher of what we've done yesterday. Feel free to hit the pause button if you want to answer these yourself. The reference table's above my head. But I'm going to get started. Based on Mendeleev's original work, the order was by atomic mass, but we have since grown and learned more enough about the atoms to put them in order of atomic number. If we're going in on group 15 in increasing atomic number, that would be from top to bottom. Non-metals on the top, metals on the bottom. We are talking group 15, so that's over on the non-metal side of the table. So we're going to go from non-metal to metalloid to metal, which exhibits both metallic and non-metallic properties. We're looking for the metalloid in the list, and of the ones shown, tellurium. So for today, I wanted to talk about these groups found in the periodic table. Why are these elements put in the same group with each other, and what starts a period on the periodic table? These questions of like, how is this structured? Because I know we've defined what groups and periods are, but we haven't really talked too much about the internal structure. To look at these elements from group 1, if you look at the last number in each of the Bohr electron configurations, it's a 1. All of these elements end with 1. Now, when you're talking about a Bohr atom, those last numbers are always found on the outside of your atom. This first one being lithium, this one being sodium. And in each case, that last number 1 is the outermost electron. It turns out that is where the bulk of the chemistry happens. We've talked about atoms and ions, and when you lose electrons, they're frequently coming from the outermost, because if you took one from the inner, the electrons would collapse down to make a new ground state. And when they are gained, obviously they have to cycle into the outermost electron shell, because in the ground state the other ones are occupied. So that was really like the similarity as you go down a group. But as you start each row, we can kind of talk about what that means. Well, we'll get to that in a little bit. Something else that we can mention in terms of the groups, Mendeleev didn't know enough about structure of the atom. That was about 50 to 60 years in front of him, maybe 40. But what he did know is, based on things like Dalton and having control over your masses, was that these elements would all end up making the same types of compounds, same type. That is to say, it says R2O and RO and R2O3. When lithium reacts with oxygen, the chemical formula for what's made is Li2O. When sodium reacts with oxygen, when potassium reacts with oxygen, when rubidium reacts with oxygen, you keep getting this 2-to-1 ratio. And that really stems from these similar outermost electrons called the valence. And it turns out that then the valence would then help dictate the chemical properties. And so we're going to say that they're similar. You might see some differences between the individual elements in the coming slides, but when I say that they're similar, it's more to say when it reacts with oxygen, it makes a compound whose chemical formula is like X2O or R2O. So let's just go through the groups in the periodic table. That's the whole goal today. I'm going to introduce you to a number of the groups and some things that might be good to know about them. There's a link to the reference tables, and also right next to that link, there's a little mini periodic table that you can keep track of where we are on the map, so to speak. So group 1 is known as the alkali metals. They are all metals with the exception of hydrogen. So there's a bit of like wishy-washy argument as to how much you want to consider hydrogen to be an alkali metal. Sometimes the periodic table actually, some periodic tables will put hydrogen way off in the middle because it just doesn't super well fit with all of the other elements. Just it's so small and so simple. But in general, the alkali metals are extremely reactive. They rust in the presence of oxygen. You can watch it happen actually on this one where you're cutting, I believe that's sodium with a knife. You can see in the split second right before it resets that the oxidation, the corrosion, is actually running down the face as it's exposed to oxygen. But these metals, they are metals, potassium, sodium. You've heard these before. Bananas contain a good amount of potassium. Salt is sodium chloride. Those are potassium and sodium in compounds. When we're talking about the elements, they're these shiny, silvery, gray substances, and when you put them in water, there's an explosive reaction between the water and the metal that creates hydrogen gas, which can make flame and explosion, and it's crazy. And because of this high reactivity, these elements are never found as elements in nature. They're always in compounds. So if you ever wanted to make or observe these elements, these samples here have to be created in a lab. There's no way to get them. You'll walk out and find some, under the ground or something. For group 2, called the Alkaline Earth Metals, they're basically the same exact thing as group 1, just a little bit less so. A little less reactive, a little less soft. You can't cut these with a butter knife as easily. Still not found as elements in nature, though. One of the key ones you can talk about is magnesium, shown up in the top. There's the ribbon. This is how you buy magnesium, so you can actually have this magnesium, and it looks like a metal. It has a very thin layer of rust on it, and so it still does react with the air. And there are some older flash bulbs in photography that used to use this bundled up magnesium, because when you light it on fire or put a lot of electricity through it, it flashes very brightly. These still do react with water, shown down here. This one's supposed to be animated. I don't know why it's not. But that's calcium, and it's bubbling away in water. So it's not quite catching on fire, but it's still reacting and still creating that hydrogen. Still can't find these as elements in nature. They're always in compounds. For groups 3 through 12, we're going to put them all together. Mostly this has to do with something of the electron structure and how the electrons are loading into the subsequently larger atoms. The transition metals are put all together because they all are kind of the same. They are higher melting, they're harder metals, sure. There are some softer ones, like gold particularly is found somewhere down here, gold, silver, platinum. But in general, iron, cobalt, manganese, chromium, these compounds are what we think of when we really think of metal. They're not super soft, but you can actually sometimes find them as elements in nature. It's more common to see that. The other thing that really distinguishes the transition metals is that when these metals make positive ions, you get multiple options are possible depending on the conditions, and those multiple options are frequently very colorful. The compounds of group 1 and 2 elements are white, always. Sodium chloride, like you picture salt, white compound. Now, not all white compounds are made of alkali metals and alkaline earth metals, but it's the other way around. That is true. But in terms of the transition metals, that weird electron structure of how they're being built will make all of these colorful compounds. And I like to usually say that the more colorful the compound, the more poisonous the compound. This one is a cobalt chloride compound, I think, with this pink color. These are chromium. I didn't get a picture of chromium element. And these are all the different compounds you get of iron. Nickels usually make blues and greens, but irons you can see a wide range, very colorful, very pretty, but then also usually pretty poisonous too. Moving right along, the groups 13 through 16 are not super heavily mentioned in the curriculum this year, but I will at least mention them. Mostly they're named for their head elements, their lead elements at the top, so the boron, carbon, nitrogen family, the oxygen family, chalcogens. These are known for being kind of, they are all in a family together because their valences, the valence electron structure is all the same. But there's a lot of variability in these families because they start as nonmetals, and in these groups, we're crossing over that staircase into metals. So we're going to see a lot of metalloids, metals, and nonmetals in these groups. Interestingly, that's where we start to say the compounds they make are similar, but like the actual properties start to vary pretty widely. One thing I did want to mention is that all three of these are carbon. This is the structure of diamond. This is the structure of fullerene. It's also called buckyballs, and you find them in carbon nanotubes. They cap the carbon nanotubes. And this is graphite. And all three of these are elemental forms of carbon, all three of them. When you have a situation where one element can take on multiple structures and get multiple different substances with different properties, we call these three substances allotropes. So graphite, you can write with a pencil because the sheets of graphite are very tough stuck together, but they slide next to each other, the two sheets, very easily. Diamond doesn't have that structure. It's a very hard substance, and then the buckyballs are kind of bouncy. It looks a little like a soccer ball because it's the same shape. Another example of allotropes would be oxygen, the air we breathe, is diatomic, and then ozone, another structure of oxygen, has three atoms of carbon stuck together in one molecule. Again, different substance, different properties, but they're both elemental forms of oxygen. In terms of the reactivity, most of these are relatively low reactivity in the grand scheme of the periodic table, with oxygen being the notable exception. It's pretty reactive, and that's how we're able to live, due to the reactivity of oxygen. Moving on to group 17, these are known as the halogens. You might be thinking of halogen lights. There are some compounds including these elements, fluorine, chlorine, bromine, iodine, and that's where that name comes from. These, similar to the alkali metals, are very reactive, not found as elements. It's interesting that on opposite ends of the extreme, you get these similar ideas. They're just very different in how they react. You get gases with chlorine and fluorine. Fluorine really doesn't exist as an element in nature, save for one case that I heard of once. It's like in certain minerals that have been isolated from the rest of the outside world. It's a very strange scenario. I can put a link to the video. But then bromine, the liquid, and iodine, the gas, you can see that iodine also undergoes something called sublimation, where the solid becomes a gas, and then you're seeing that purple gas, and then this top beaker is cold, and so it recrystallizes back into a solid called deposition. Finally, the group 18 elements, we're done working our way from left to right. The noble gases, so called because they are all gases, they're found at the end of each period, right? This is the last element before we move on to the next row. And they are called noble because they are unreactive or inert with all other chemicals. It's like they don't want to bother to interact with the lowly common elements found on the rest of the periodic table. Kind of hard to show pictures of them because they're all clear, colorless, odorless gases. These exist as monatomic in nature, as in molecules of only one atom apiece. So it's kind of like the complete opposite of both group 1 and group 17 that are all super reactive and never exist as elements. The noble gases only exist as elements in nature. It is possible for some of the larger noble gases to, under extreme conditions, end up getting a reaction where a compound gets made, but it's unstable. Some of the common uses are, what you see in the image here is xenon gas, the heaviest non-radioactive noble gas, is way more dense than air, about 5 or 6 times more dense than air. So when you pour it into a container, it actually does kind of pour like a liquid does, and you can float certain objects on that air if you've got the right buoyancy in place, and so the person scooping the heavier air into the aluminum boat. Or because they're so unreactive, you can pass a lot of electricity through them and you get a good excitation emission process going. And so a lot of the neon lights that you're familiar with seeing contain noble gases. In fact, neon has that common red color that you're used to seeing, that red-orange. Any other color neon light is actually some other gas, usually a noble gas. It is worth saying that if you do look at each of the groups, obviously, like I said, the number of valence electrons is common within the group. And that number for the noble gases is 8. And it does seem to be that after you hit 8 electrons, there is reason for the next electron to actually fill into the next highest energy level, which is why we've decided to then start a new row. So neon has 2,8 as its electron configuration. The next one, sodium, is 2,8,1. And so you end up seeing that new row starting each time. And then finally, I wanted to mention the bottom two, those rows that frequently get not mentioned. They're either called Actinide and Lanthanide or Actinoid and Lanthanoid series, depending on which book you're reading and who's talking. They're known as the rare earth metals because, well, they're rare. The Lanthanides, those are the ones found in the upper of the two rows. Those are really the rare earth metals, and they're found. They have many uses, but they're many like bespoke uses of things that you don't really realize until suddenly you discover something, and then you need a bunch of it. Good lasers and neodymium magnets, and a lot of materials then found in modern electronics will utilize those elements. And then the actinides don't have a ton of uses because largely they are all radioactive and many are synthetic. So actually, well, they might not. No, I think they're all radioactive. So really, those don't exist much in nature at all, and when they do exist, they're created in a lab through some sort of particle accelerator or something similar. So to round all of this information off, general ideas is groups of the periodic table are associated with each other because of their valence electrons and how they chemically react. Not to say they react the same way, but in terms of the molecules and compounds they make, you see a similarity there. Many of the groups are named for the element at the top, or some of them have some older names, but in general you still see that familiarity of properties. Thanks for watching.